All right, so we're going to talk about energy here for a few minutes. If you were in physics class and you looked in the back of the physics book for a definition for energy, what do you think it would tell you? It's ability to do work. And in physics, the definition of work is maybe a little different than you might think. In physics, to do work, what has to happen? Something has to move. Work is about moving things. The equation for work in physics is force times what? Distance. Things have to move. So sometimes we might define energy as the ability to make things move. That's another way of thinking about it. It's the ability to make things move. What you should realize is that the sun on Earth, the sun is the ultimate source of all the Earth's energy, with maybe one exception. What might that exception be? Where on Earth might there be some energy that didn't come from the sun in one way or another? The thermal stuff from the core, right? Like volcano kind of stuff. The vents, like at the Yellowstone, the hot spring kinds of things, geyser kinds of stuff. That came from radioactive and frictional heat from the core of the Earth, right? Not so much from the sun. But everything else, in one way or another on Earth, comes from the sun. Now when we talk about energy on Earth, we usually talk about two kinds, kinetic and potential. Beaver back there asked about K-I-N earlier today. K-I-N means what? Moving. Okay? Kinetic energy is the energy of motion. It's the energy that moving things out. Potential, on the other hand, is just what it sounds like. It's stored. It's energy that you got stored in some way or another. Now, in a physics class, the main kind of potential energy we would talk about is gravitational. That if I took this stapler and I held it here over Megan's head, if I dropped it from this very low height, it might sting a little bit, but Megan's going to be okay, right? But if I took it up on an airplane and there was no ceiling here, and I dropped it, Megan's not going to be okay, right? Because the higher this thing gets above ground, what does it gain? More and more gravitational potential energy. And as it drops, that gravitational potential energy is converted into what? Kinetic energy, and it starts moving faster and faster and faster and faster. In this class, we're not going to talk too much about gravitational potential energy. We're talking more about chemicals. In biology, the kind of potential energy that we're more concerned with is chemical potential energy. Yeah, but it's also biology. Chemistry's everywhere. You can't get away from chemistry. In this class, chemical potential energy, the energy stored inside a chemical bond. That's where energy is stored in chemicals, mostly. It's in the bonds, right? Energy stored in bonds. Now, a couple of other things related to energy we need to talk about are these laws of thermodynamics. The first law of thermodynamics you've all heard of before. You may not have ever heard it called that before. You probably heard it called the law of conservation of energy. That's the idea that you cannot do what with energy? You can't create it, you can't destroy it, but you can do what with it? You can convert it from one kind of energy to another. Like this energy that I was talking about. Right now, what kind of energy is allowing me to lift this stapler? Where did I get the energy to be able to do that? I got it from food. I got it from chemical energy, right? That chemical energy is now allowing me to, I'm converting that chemical energy into what right now? Gravitational potential. And if I let it go, it's going to convert itself again into kinetic. What's it going to be when it hits Megan's head and stops? It's going to create a couple things. It's not going to go away. It's not going to be moving. It's not going to be above the ground anymore. That energy became two things when it bounced off Megan's head. Number one, it probably made a sound. Sound is energy, right? It also probably created what? As it was falling and as it bounced off Megan's head. Heat. Heat, thermal energy is another kind of energy. So energy can be converted from one form to another. You can't make it or you can't destroy it. That's the first law of thermodynamics, or the law of conservation of energy. The second law is a little bit more complicated. And it's one you may not have heard so much about. It's about a concept called entropy. Anybody ever heard of entropy before? Entropy is like chaos, disorder. The second law of thermodynamics basically says this, that energy must be added to a system in order to maintain homeostasis. If you don't add energy, what happens to things? They fall apart. They become chaotic. They go into a state of entropy. For example, let's say that Chad there built a brand new house. And then he went bankrupt. Okay? And they took his house away from him. But the bank could never sell the house. So the house just sat there for 20 years. It just sits up on a hill. Chaz comes back 20 years later. He got a job. You know, after 20 years of unemployment, he got a job. He decides he's going to go buy that house back from the bank. But it's been sitting there for 20 years. Nobody's been to it. Nobody's touched it. Nobody's painted it. Nobody's put any nails in it. What's that house going to look like 20 years later? It's going to be in a state of disorder, chaos, disrepair. That would not only happen to a house, it would happen to your body. If you stop adding energy to your body, it's going to start falling apart. It's going to become chaotic. That's the second law of thermodynamics. Without energy being added, a system falls apart. It goes into the state of entropy, the state of chaos. Our body's main kind of energy, we know, is ATP, adenosine triphosphate. Made during what process? Cellular respiration. Cell respiration takes energy from the food we eat and stores it in this chemical, ATP. In terms of the structure of ATP, let's see if I have a picture on here of ATP. I'm not sure if I do or not. Yeah, here's a picture of ATP. What kind of chemical is ATP? Of those four big groups of macromolecules, which one does ATP fit into? Those four groups, remember, are carbohydrates, nucleic acids, proteins, and lipids. This is a nucleic acid. It's in the same group as DNA and RNA. And also, what second messenger molecule? CAMP, right? Nucleic acid. Nucleic acids are all made out of three things. Anytime we see rings like this, the green thing here, what is that? It's sugar. In ATP, that sugar is ribose, the same sugar found in ATP. These over here are what? Phosphate groups. And then this thing over here is what? A nitrogenous base. And in ATP, that nitrogenous base is, guess what? Adenine. In GTP, it would be what? Guanine. Same kind of thing, though. But as we see here, ATP, if we go this way in our cycle, here ATP is getting hydrolyzed. Hydrolysis means it's being broken, split, right? And when we split it, all we split off is this last phosphate. There's a typo in this picture. That should not say ATP there. That should say what? It should say ADP. Because if we take ATP and we split it, now we have adenine diphosphate plus the phosphate we took off plus what else that comes out. Energy is released. Now the ADP and the P, you should think of those like dead rechargeable batteries. And what's the process in your body that recharges your dead ADP and P? Cell respiration. And the energy to recharge them comes from where? Food. Okay? So here we're seeing the recharging process happening. Here's the using the energy. Here's the recharging the batteries. This would be hydrolysis. This would be cell respiration. So that's our ATP cycle. Adenosine triphosphate up here. Adenosine diphosphate down here. And what's the other version of ATP that we talked about? CAMP, which is adenosine monophosphate. That's our second messenger molecule. Let's go back a slide for a second. Something kind of scary about ATP. ATP is our body's energy currency. It's the energy that we can use. It powers everything in your body. But the scary thing about it is this right here. You only have enough ATP stored up in your body to last you about 20 seconds. Which means if cell respiration stops, 20 seconds later, you're dead. And there's no reviving you. When cell respiration stops, it's over. You're gone. 20 seconds. Now, a lot of people have a hard time understanding that because they're thinking, hey, I can hold my breath underwater for a minute and a half. Some people can do that longer, right? So why don't they die? When you're holding your breath, are you out of oxygen? There's still oxygen in your lungs, right? There's still oxygen where? In your blood. As long as you have oxygen available, you can still do what? Cell respiration, okay? It's when you run out of oxygen. That's when the 20-second time limit starts to run, right? And for some people, I saw a thing of the deep diving guy the other day. He was underwater for like 4 or 5 minutes. No scuba mask or anything. He just had really good lungs. He could hold his breath for a long time. But that time limit starts when the oxygen runs out because oxygen is required to do aerobic cell respiration, right? When that runs out, you got about 20 seconds. And then it's over for you. Which is scary. To get the energy out of ATP, we have to hydrolyze it. We have to break off. What are we breaking off when we hydrolyze it? The last phosphate, right? We take off that last phosphate. What enzyme often does that for us? What enzyme takes the phosphate from ATP and gives it to something else? Kinases, right? Protein kinases do that for us. Let's talk about these two kinds of reactions right here, exergonic and endergonic. Now in chemistry, you probably called exergonic reactions exothermic. You probably use that word instead. In chemistry class, what was an exothermic reaction? It's one that gave off energy as it was happening. There's a lot of things like putting zinc in hydrochloric acid. Most all of you did that, right? Put a piece of zinc in hydrochloric acid. What happened to the test tube when you did that? It got really, really hot. Like so hot it could burn you. That's an exothermic reaction. They give off heat as it's happening. Give off energy. Endergonic, you probably call it endothermic. They're reactions that take in energy. Energy has to be supplied to them to make them happen. If an endergonic reaction was happening in a test tube, what would it feel like? It'd feel cold because they're sucking in energy from the environment. Does that make sense? So, endergonic reactions in your body, where does the energy come from to make them happen? How do you start up your body's endergonic reactions? What provides the activation energy to get them going? ATP. ATP is the battery that starts your body's endergonic reactions. Without ATP, these don't happen. Something has to give them energy, and it's ATP that gives them energy to make them happen.